Good morning, everyone. I am Davide Zanchettin from the University Ca' Foscari of Venice, and today I will outline some results and also the general framework of the project IPSODES, which stands for Investigating the Predictability of the Southern Ocean Dynamics through Ensemble Simulation Hindcasts. IPSODES is a project funded by the Italian National Program of Researches in Antarctica, and it is also an YOPP-endorsed project. It is run in collaboration between University Ca' Foscari of Venice, the University Partenope of Naples, and also the Institute of Marine Sciences of the National Research Council of Italy. The Southern Ocean dynamics are known to display a very energetic variability over a wide range of spatial and temporal scales. This is well illustrated by this simulation with FESOM in a high-resolution version of the model that allows for small-scale features to emerge, and we recognize that the Southern Ocean is peppered by meandering currents and mesoscale gyres that develop, are transported, and then dissipate. So a substantial fraction of this type of variability is known to be intrinsic and basically chaotic, which implies poor predictability. Also, current climate models typically have an ocean component that lack the necessary resolution to produce spontaneously this type of variability, which implies also that Southern Ocean dynamics are a challenge in their simulation in terms of trends and variability for current generation climate models. Therefore, IPSODES is aimed at improving process understanding concerning the predictability of the Southern Ocean dynamics through ensemble simulation hindcasts, tackling different aspects that relate to ocean, climate, and environment. And for each, we use specific tools. In the case of the oceanic component, we use ensemble simulation with conducted within IPSODES with the Princeton Ocean Model, and POM has been implemented here in two versions, one with a domain covering the whole Southern Ocean and one with a reduced domain centered at the Ross Sea longitude that you see illustrated in the maps in this slide. Overall, ensemble simulation are hindcasts, 18-year long, forced by ECMWF reanalysis, and all ensemble simulation members differ only by their initialization. So a tiny perturbation is introduced in the initial condition, and the experimental design for all simulations is otherwise identical. So to illustrate qualitatively how intrinsic ocean variability emerges from this approach, I show you now two snapshots from the POM simulation that refer to the same time instant but belong to two ensemble simulation members. As you see, the two maps agree on the gross features of the circulation, but there are also specificities. For example, the one highlighted by the red circle, we see that circulation is organized differently in these two simulations. In the right case, for example, we have just one branch of the current. In the left map, we have that the circulation is basically characterized by retroflexion, maybe, or even divergent current. So this is, as I said, thought to be an expression of intrinsic ocean variability. In IPSODES, we will tackle this also quantitatively and also by drawing from methods of dynamical system theory. And ultimately, the idea is to be able to define, characterize the so-called pullback attractor of the system. Concerning climatic aspects, we use Coupled Global Atmosphere Ocean Sea Ice Model ensemble simulation run with the decadal climate prediction system developed within the German project MICLIP, which is based on the Max Planck Institute Air System model in its high-resolution version, where MPIOM is run, the ocean model is run in an eddy-permitting configuration. Still, there are substantial biases that concern, for instance, transport through the Drake Passage and sea ice concentration as illustrated in the map of sea ice fraction bias in the right of this slide. We use an assimilation run from 1958 to 2018, and 5 Ensemble Hindcasts initialized each November 1st from 1958 to 2017. We use bias-corrected data and neglect data before 1979, as Antarctic sea ice data are relaxed to climatology during this period. The idea is to, first of all, identify intrinsic ocean variability, in this case in terms of kinetic energy of the Southern Ocean, despite the fact that we are aware that this might also reflect an imprint of atmospheric forcing in this type of ensemble simulations. Then we define, or we identify composites within a simulation run and hindcasts around strong and weak states of kinetic energy. Then we determine if ensemble anomalies of relevant physical variables are statistically different between the two groups. And in the example I will illustrate shortly, we focus on Antarctic sea ice concentration. In this case, the grouping of kinetic energy is based on the austral summer, so specifically on the period January-February, which is a period of the year when we have comparatively weaker energy in the Southern Ocean and also less interannual variability, as illustrated in the figure to the left. But in this case, we are closer to the initialization of the Hindcast, so that occurs in this case in the preceding November. In the figure to the right, you see the time series of JF Southern Ocean kinetic energy and also the years that have been used for the composite analysis. So concerning the implications of kinetic energy for the southern, kinetic energy in the Southern Ocean for Antarctic sea ice concentration and its predictability, what we plot here is are differences between sea ice concentration data under strong kinetic energy minus sea ice concentration data under weak kinetic energy for a simulation run in the left panels and for the hindcasts in the right panels. So any significant signal that is plotted in the left, so for the assimilation, is an indication of potential predictability of sea ice dynamics related to kinetic energy. On the other hand, for the hindcasts, we can have a clue about the forecast skills of the decadal prediction system, again concerning sea ice dynamics related to kinetic energy. So what we see is that overall there is some potential predictability. There are some patterns that recurrently emerge as we progress through the hindcast time. For example, in the first austral winter, here in the simulation run, we have consistently a sea ice increase, especially in the eastern hemisphere and at the margins of the Ross Sea. This is clearly not reflected in the anomalous patterns for the hindcasts, which implies that if there is some potential predictability, then the forecast skills are poor, if not misleading, for example, as in the case of the anomalies found in the Drake Passage and in the Weddell Sea. But also closer to the initialization, for example, in the first hindcast January, we see that despite there is some convergence between indication in assimilation and hindcast results, that there is a sea ice decline in the Weddell Sea. This occurs close to the Antarctic Peninsula in the case of the hindcast, whereas it is more in the open sea in the assimilation case. So overall, my conclusion is that there is some potential predictability, but there seems to be poor forecast skills as well. To conclude, I would like to provide you some information about what are the expected tangible outcomes of IPSODES, so the deliverables. We plan to deliver outputs of ensemble simulations of an eddy-permitting ocean model, POM, applied to the Southern Ocean domain. synthesis data and metrics to assess variability and predictability of the Southern Ocean from near-term ensemble climate predictions, including, for instance, strength and variability of the ACC, eddy kinetic energy, and sea ice parameters. And concerning the environmental aspects relevant for Southern Ocean dynamics, we plan to produce Lagrangian trajectories obtained from the Eulerian velocity fields from our POM simulations that will be initiated at the location where marine debris have been observed experimentally to accumulate. So I would like to conclude here. I thank you very much for your attention, and I'm looking forward of taking any question concerning the analysis, the results, or overall the IPSODES project. Thank you.
So Davide is online. Prepare for your questions. So I might have one, Davide, if you can hear me. So the link between the mesoscale activity of the Southern Ocean and sea ice, is it mostly controlled by the transport of sea ice or heat fluxes, melting or forming sea ice, or both?
I think it's a contribution of both. And just to remind you that our simulations that are eddy resolving do not include sea ice, so we focus there on the atmospheric forcing. So there is still work to do.